So, continuing with the topic of measurements, let's now learn about actual measurements of length using several instruments like Vernier scale and screw gauge, measurement of volume, mass, and time. So, whenever we have to measure something, we need an instrument, and that instrument has got a certain characteristic of precision. Think about your usual scale, which you have which you carry in your geometry box. It may be 6 inches long or 12 inches long. It has got graduations in centimeters and further in millimeters. So the smallest division is a millimeter, and that is called the least count, the smallest division that can be read in an instrument. So using that, if you have to measure the length of this particular stick, you align the zero of your scale with one edge, and the other edge is you have to read. Now you can see here that this particular point is 1.6 centimeter. So the reading is definitely more than 6 but less than 1.7. All we can say is this: it is more than 1.6 and less than 1.7. Exact measurement, can we say 1.63 for example, or 1.68? No, we can't, because there's no such division to be read. So the precision, that is the degree of resolution to which you can read, is limited by the least count. So the smaller the least count that an instrument has, the more precise it will be. How can we improve this precision? We can improve it by using a different instrument called the Vernier scale, which has got a least count of zero point 0.1 millimeter. This is the smallest division is 1 millimeter, but in Vernier, the least count becomes zero point 0.1. In a micrometer screw gauge, it becomes even better, 0.01 millimeter. Before we go to Vernier scale, let us learn about parallax, and that is a kind of error that we must avoid while reading. So suppose we are using our normal meter scale and we are measuring the length of this red line, and we find we have to read this position of this last edge. Depends where we place our eye. If we place our eye directly above, then we can see that it is 4.8 centimeter. But if you place it here, then the division that coincides is this 5 centimeter mark. If we keep it to the left, then the division that coincides is the 4.6 centimeter mark. In each case, we have an error, and that parallax error should be avoided. That is because of the thickness of this particular scale. So to avoid it, the wrong method is that you keep it like this and you read. Then there's a chance of a parallax error depending on where you place your eye. But if you turn the scale and keep it vertical, then the chance of such an error is minimized, right? So parallax error should be avoided. Now let's learn about the vernier. It is an instrument which has got two scales, a main scale and a vernier scale. This is the main scale, which typically has 1 millimeter divisions. The smallest division is 1 millimeter typically, and that is fixed. There's a jaw, there are two jaws here. This jaw is fixed and this is movable. Whatever we want to measure, we place it here. Now, when there's nothing placed, then the two jaws are touching each other, and then there's a zero of the main scale, and this vernier scale, this particular point would be sitting here actually, and then there's a zero of the vernier scale which will be coinciding with this. That is the starting point. Now you move the vernier and place your object whose length you want to measure. So that means how much distance the vernier has moved to the right is what we have to see. So these are the jaws which are used to measure the outer dimensions like the length of a stick. Then if you want to measure the inner dimensions like the diameter of a cup or a glass, then we use these jaws for measuring inner dimensions. And once we have brought the vernier to the right point, then we tighten the screws so that it doesn't move. And then we have a stem which is used for measuring depth. So let us see how this scale gives us a least count of 0.1 millimeter. The key thing is that the vernier has got some number of divisions. In this case, you can see This is the Vernier scale. It has got 10 divisions. And we have aligned, let's say, the 1 centimeter mark with the zero of the vernier. Then we see that the ninth division, starting from here, beginning, the ninth division of the main scale coincides with the 10th division of the vernier. That means 10 vernier scale division equal to 9 main scale divisions. And one main scale division is 1 millimeter. So, what is the smallest movement of the vernier from this position that we can detect with our normal naked eye? That would be the least count. So, what is the gap between the first division of the main scale and the first division of the vernier? What is the gap between the two? Well, from here to here, this is main scale, so it is 1 millimeter. And from here to here, it is one division of the vernier. Now, one vernier scale division is 9 by 10 of a main scale. So 0.9 MSD or 1 MSD is 1 mm. So 1 VSD is 0.9 mm. Therefore, this is 0.9 mm. The gap between them is 1 mm minus zero point 0.9, that is 0.1 mm, and that is the least count. So if this vernier were to move to the right like this, then the smallest movement we can detect is this zero point 0.1 mm. And when that happens, then these two lines would be coinciding. Suppose a greater length is moved, then some other division will coincide. So suppose the fifth vernier scale coincides with any main scale division. That means this particular point has moved and coincided with this. Then how much has it moved? The gap between fifth main scale and fifth vernier scale would be zero point 0.1 mm into 5. So that is 0.5 mm, right? So let us see how we can analyze the least count further and then see how we can read off a vernier. So the definition of least count is one main scale division minus one vernier scale division. In this case, it turns out to be 0.1 mm. Now, the least count for a vernier is also called vernier constant. It can be written in a more simple manner. That is the value of one main scale division divided by number of divisions on the vernier. In this case, this was 1 millimeter and there were 10 divisions on the vernier, so it is 0.1 mm. Now this holds if n divisions of vernier coincide with n minus 1 division of main scale. Here it was 10 coinciding with 9. If we have such a situation that n divisions of vernier coincides with n minus 1 division of main scale, then we have this formula. Let us derive it. This very simple derivation. Let x equal to value of one main scale division. And then n divisions of vernier equal to n minus 1 division of main scale. Therefore, value of n vernier divisions will be n minus 1 divisions of main scale. That means each main scale is x. So the value of n vernier is n minus 1 into x. Value of one vernier division is divide that by n. The whole thing divided by n. Least count is 1 MSD minus 1 VSD. 1 MSD is x and 1 VSD is all of this, that is x by n. What is x? Value of 1 MSD. What is n? Number of divisions on the vernier scale. So that is another way of a simpler way of writing it. But please remember, this only works if n divisions of vernier coincide with n minus 1 division of main scale, which is the usual case as well. So let's see this reading. The zero of the vernier has come to this point. So the reading is definitely more than this point, which is 3.4, and definitely less than this point, which is 3.5. But how much? We need this value. We need this value. And you find that the third vernier is coinciding with any main scale division. So that means this reading, this value is called the vernier reading, vernier scale reading. That means if the third is coinciding, then the vernier has moved by a distance, the least count into 3. So we can call it the pth division of the vernier is coinciding. So the vernier scale reading is least count into p. Least count into p. So vernier reading is least count into p. Least count is 0.1 mm usually, and p is 3, so 0.3 mm. The net reading is the main scale reading plus the vernier scale reading. Main scale reading is 3.4 centimeter and the vernier scale reading is zero point 0.3 millimeter or zero point 0.03 centimeter. So 3.43 centimeter. You see, we are able to very precisely tell about the second digit after the decimal when we are reading in centimeters. The least count has improved 10 times over the meter scale. The use of the stem of the strip is to measure the depth. Now the stem and the strip is connected to the vernier. So if the vernier is touching, the two jaws are touching, then the stem is also completely inside. Suppose we want to measure the depth of a tumbler, we put the vernier upside down and the two jaws are together. Then we extend the jaws and let the stem touch the bottom of the tumbler. The distance moved by the stem is also the distance moved by the vernier, which is what you want to measure. So that is the use of the stem or the strip. Zero error can occur in verniers. That is when the zero of the main scale and the vernier they are not coinciding. Then we have to do a compensation. See here, we have the two jaws J1, J2 touching each other. In such a case, the 0 and 0 of the two scales should be coinciding, but the 0 is ahead. The 0 of the vernier is ahead. It should not have been ahead. It is already ahead. So now when you insert something between the two jaws, what is already ahead is being added to your reading. So therefore, you should subtract that much. From your reading, you have to subtract the amount by which the 0 of the vernier was ahead of the 0 of the main scale. How much is it ahead? In this particular case, we find the sixth one is coinciding. So the vernier has moved by 6 divisions. That means it has moved by the least count into 6. And that is the error which is called a positive error. So the least count is zero point 0.1 mm usually, and 6th reading is coinciding. So zero point 0.6 mm is the error, which is a positive error. Sometimes the 0 of the vernier can be behind the 0 of the main scale. That is a negative error, right? So here you see the 0 again are not coinciding. The 0 of the vernier is behind. So the reading that you get will be a little bit less. How much less? By the same amount that the two zeros are displaced from one another. This is a negative error. Again, we find the sixth one is coinciding. So is the error again zero point 0.6 mm? No. How much it has moved to the left now is what we have to see. So earlier, the 10th division of the vernier would be coinciding with some main scale division. And now when we move it to the left, then how much it has moved to the left, we have to see which division from the right is coinciding, not from the left. And the fourth division is coinciding from the left. Therefore, the error is zero point 0.4 mm with a negative sign. It's a negative error. This has to be added to the observed reading. The correct reading is the correct length is the observed length for what you read minus the zero error with this sign. So if it is a negative error, when you put the negative sign, then the correct length becomes more than the observed length because there are two minus signs. When it is a positive error, then the zero error is positive here. So the correct length is a little bit less than the observed length. So make a note of this. All right. Then we have our even better instrument, which is called a micrometer screw gauge, which can be even used to measure the diameter of a wire, a thin wire, whose diameter may be even less than zero point 0.1 millimeter. So the least count of this usually is zero point 0.01 millimeter. It works on a different principle. Okay. And that is what we are going to take up in the next session.